Hi everybody, it's Mr. Neff here, and today I want to talk about Newton's third law. This law is known as the law of interaction or the law of force pairs. It always applies. First law applies to cases where the forces are canceling out, balancing out. Second law applies to forces that aren't. But the third law always applies. So I might say a problem is more of a first law problem or more of a second law problem, but it's going to be always a third law problem too, and that's an important thing. Now, everybody knows the third law. For every action, there's an equal and opposite reaction. Think of how easy it would be to find somebody out in public that could finish that statement for you. For every action, there's an equal and opposite reaction. For every action, every time, no, never ever saw a counterexample to this. There's always an equal but opposite reaction. We got this kid right here, right? And this kid is, well, he's sitting there. He's kind of closed off. He looks like he might be angry or upset or something like that. He probably didn't do his prep, And he's got the force of gravity weighing him down. He like looking at him, he might have other things weighing him down too, but he's got the force of gravity weighing him down. Now, the good thing though is he's sitting on something solid there, it looks like, and he's not falling down. Is he not falling down because of the third law? Is it the third law that's not making his bad day worse? Is it? See, I'll come back to that. An important consequence to all this, that every time you have an action, there's an equal and opposite reaction, is that forces always occur in pairs. And finding the action from the reaction or vice versa is so easy. Here I have a ball being hit by a bat. Bat hits ball. That's an action. The reaction to that is, well, people sometimes confuse the effect of the action for the reaction. And that's where maybe the naming this reaction might not have been the best choice. The reaction is not ball flies away. That's the effect of the action. The reaction is the ball hits the bat. It's so much simpler than you thought. That's all it is. You could put directions on there. You could say the bat hits the ball to the right. And so the ball hits the bat to the left. It's as simple as that. And so any force that you can think of as one force on another object, well, that's going to have a reaction to it, including gravity. And so I come back up to this guy and I say, hey, is the reaction to this force of gravity the normal force? Is that the force that's holding him up? Because we say that he's not falling down because there's a normal force on him that's the same size as the force of gravity, right? Those two are the same size, and so he doesn't fall down. Well, what is the reaction force to the force of gravity? Well, think about what the force of gravity is. That's the interaction between two objects too. That's really the force of the earth on the boy. And the earth is pulling him down. Well, what's the reaction to that? Well, if you follow that bat and ball example, the reaction would be the boy pulls on the earth. You might say, come on, man, that's not what happens. It is too. It is what happens. If you believe that the third law is a thing, then for every action, including earth on boy, there's an equal and opposite reaction. Is boy on earth. Now, what's that boy weigh? I don't know. Maybe he weighs 130 pounds. Maybe. Well, 130 pounds of force is pretty effective on a boy, on this much mass. But 130 pounds, how effective is that on this much mass, the giant earth, huh? Is that force still there? You bet it is. It's the same size, 130 pounds. Force of gravity, it's also a force of gravity. But it's just not very effective on that much. The acceleration here, the acceleration that force of gravity gives that much mass, well, we know the acceleration is 9.8. Well, the acceleration that that same force gives this much mass is practically nothing, 0.00000. So no, it's not that. See, in fact, it's not that it could never be the reason that he's not falling down, because it's not even on the same object. No, it's the normal force that's the reason that he's not falling down, and that normal force is just because the force of gravity is allowing him to bend the surface of his chair and it's trying to stay straight. Both of those can cancel each other out because they're both forces on him. There we are. Now, if I wanted to just check for understanding on that, I could say athlete pushes bar upwards, and you could say bar pushes athlete downwards. And I could say bowling ball pushes pin rightwards, and you could say pin pushes bowling ball leftwards. And I could say compressed air pushes balloon wall outwards, and you could say balloon wall pushes compressed air inwards. So it's pretty easy to get those. Now, sometimes people, again, confuse the thing and its effect. Here I have a bug that's hitting the windshield of a bus. Bus hits bug. Reaction, bug hits bus. You say, hey, I was born for this. I know all about this, right? This is easy. Okay, now let me ask you, which one of those two is a bigger force? Because one of them destroys the other. One of the things is destroyed by the force, and the other thing is not destroyed by the force. So which one of those is bigger? Well, it turns out they're the same. Why are they the same? Because Newton told us for every action there's an equal but opposite reaction. But you might say, well, then why does the bus hitting the bug, why does that have a huge effect? Well, why are bugs more delicate than buses? Maybe that hits with a 2-pound force, and a 2-pound force for a bug is no good. But a 2-pound force on a bus, well, it's not great, but it's, just kind of, wish it didn't happen, but it's not gonna break a windshield, if you know what I mean. So don't confuse the size of the force with the effect of the force, because there's more going on there. Okay. Here's a similar thing. Here's a cartoon of someone firing a rifle, and the rifle pushes the bullet. And the reaction to that, of course, is the bullet pushing rifle. Easy enough. Now I say, which one of those is greater? And I'll point something out to you. The bullet goes with an unbelievable acceleration. And the rifle, it goes, I mean, if you've ever done this, you know that the rifle does accelerate, but the acceleration is way smaller relative. How come? How come? Well, two things. Number one, you got the same size force. Force on the bullet, force on the rifle, same size. But the rifle is so much more massive, and the bullet is so much less massive. So the acceleration on the bullet is so much greater, and the acceleration on the rifle is so much smaller. Not just that, but what else? The bullet's not being held by anything or anyone. The rifle is. This fella is pushing forward on the rifle, right? And so you've got an acceleration. Now, acceleration on the rifle, that's not just a function of one force, it's a function of two forces, huh? And so now there's a force backwards, but there's also this force forwards too, see? And so all that to say, there's a net force that determines the acceleration, not just the one force. So which force is greater? They're the same. Why aren't the effects the same? Well, the masses are different, plus there's more forces on the rifle. Okay. All that to say this, don't misjudge a force's size because of its effect. Here's a classic problem. This will show up in every physics book. And it talks about a horse and a wagon. And in this version of it, the horse is asked to pull a wagon, and the horse says, I can't pull the wagon, because if I pull on the wagon's going to pull back on me with an equal force. And so how could I possibly pull the wagon? So I won't even try. Now, if you don't understand this very well, that could seem compelling. The horse is going to pull on the wagon, definitely. And the wagon is going to pull backwards on the horse with exactly the same size force. Definitely. I put it on the horse. Definitely, right? And so it would look like that would cancel out. In fact, we've talked about in class, you have an object and a force this way and a force that way, and they're the same size. And we say no acceleration. And so you might say, well, that's the same thing here. But do you see how this situation with what I drew in the free body diagram, that is not the same as what I have for the horse and the cart? You see why? See, these two forces, the green and the yellow, are on different objects. And so they don't cancel each other out. Forces on different objects can't cancel each other out, you see? And so in the end, if action and reaction were on the same object, they would always cancel each other out, and we wouldn't have net force. And I'm not even sure that world would be sustainable. No, they're never going to be on the same object, because think, you got to switch the order of those nouns, and so they're never going to cancel each other out. So sounds compelling at first, but definitely not sound physics.